Hello everyone, and welcome back to the Proactive Learning YouTube channel. Today we're going through question 21 from the 2017 higher paper, paper 2. So, the question tells us we have three identical circles inside a rectangle. Each circle touches the other two circles and the side of the rectangle as shown. The radius of each circle is 24 millimeters, and we want to work out the area of the rectangle. So first thing is, to find the area of the rectangle, we want to know what these two lengths are. So what one of the sides is and what another one of the sides is. So let's see if we can figure these two out. The first thing that comes straight to mind is we know what the radius is for each of these circles. So if we look, we can sort of connect four of these radiuses together, or radii, to form one of the lengths. So if each one of these radiuses or radii is 24 millimeters, all we have to do is times 24 by 4, and that gets us one of the lengths. So if we times 24 by 4, we get 96 millimeters. So now we know what one of the lengths are, so 96 millimeters. So from here, the next thing that we need to think about is, how do we find the second length that we need to find? How do we find this here? One thing that might come to mind is, let's do exactly the same thing that we did earlier. Let's try and add up these radii. So we have one radius, a second radius, then here we have a third radius and a fourth radius. So we might be thinking, that's it, that's the question done. We add four of these radii together, then we get the second length. But the only problem here is there is a little bit of overlap, which means our answer isn't quite right. So here is where one of our radiuses lines up, and this is where the second radius lines up. Here, we've got this gap. So in other words, timesing 24 by 4 doesn't give us the correct length here. So the next thing that we need to think about is, what are some clever tricks that we know we can use? So if we rub out this work and have a quick think about what else we've been given in the question. So we've been told that each of these three circles are the same. So in other words, this radius here is exactly the same to this radius here, which is exactly the same to this radius here, exactly the same as this radius, exactly the same as this radius, and once again, exactly the same as this radius here. So in other words, we've sort of made ourselves a triangle, haven't we? But what type of triangle is this? Is this an equilateral triangle? Is it an isosceles? What could it be? And the key thing that we need to understand here is, each of the sides is made up of two radius lengths. So in other words, our triangle has the same length for each of its sides. So it's an equilateral triangle. But how does that help us? So what if this is a triangle where all of the sides have the same length? How does that help us? The main way that it helps us is if we think about how we can use this triangle. So if we have a triangle like this, what we can do from here is think, we've got one radius here, we've got the entire length of the triangle here, or height in other words, and we have another radius here. And that shows what this length here is if we add those together. But the next question is, we know what this is, or what the length of this line here is. We know it's 24 millimeters. We know this as well for this length here. We know this is also 24 millimeters. But how do we find out what this green length here is? Now, using some space given on the paper, let's redraw this triangle. To be specific, this equilateral triangle. So let's write down what the lengths of the sides are. So if each side is 2 lots of the radius, it's 24 times 2, isn't it? And this is equal to 48 millimeters. So each of our sides has a length of 48 millimeters. But how does that help us to find what this dotted length here is? One way you could think about it is, if we have a length we don't know, how do we usually find it? We usually find it using trigonometry, don't we? Using sine, using cos, using tan, using tricks like SOHCAHTOA as well. But there's a nice, easier way you could think about it. Now, if we have a dotted line here, this is going through exactly the middle of the triangle, isn't it? So in other words, what is the length of this bit here? It's just one lot of the radius, isn't it? So this length is 24 millimeters, and this is 24 millimeters. Now in this case, if we think about the left-hand side triangle on its own, we'll call it triangle number 1. Let's redraw that. So we have half of that equilateral triangle, but here we know what one of the lengths is. Lengths is 24 millimeters. We know what another side is, 48 millimeters. So here, to find out this unknown length, let's use trigonometry. So this is our opposite to our angle, and we have our hypotenuse. So let's use sine. So sine of 60 is equal to our opposite, which we don't know, over our hypotenuse, which is 48. Now here, what's the opposite of dividing by 48? It's timesing by 48. So let's times both sides by 48. So as a result, our unknown side is now equal to 48 lots of sine 60. Now, what is sine 60? So from our knowledge, we should know that sine 60 is a particular angle. But what could it be? Now, when it comes to sine 60, you could use many different ways to remember it. Personally, for me, I like to just memorize it. So sine of 60 is just root 3 over 2. And that is getting times by 48. And that simplifies down to 24 root 3. So our unknown side is 24 root 3 millimeters long. So last but not least, let's look back at how we find the second length of our rectangle. So we had this unknown side that we now know is 24 root 3, but then we have to add 2 lots of 24 to it. So if we add 2 lots of 24 to it, what do we get? So if we put this into our calculator, 24 root 3, then we want to add 24 and add 24 again. We get 89.569 to 3 decimal places. But now we're not quite done yet, are we? We want to find the area of the rectangle itself. So this is one of our sides, and all we need to do is times it by 96 millimeters. And what does that get us if we put that into our calculator? That gets us 8,598.645 millimeters squared, which we'll write down on our dotted line. Before we do so, let's see if the examiner wants us to write it to a particular degree of accuracy, which they do. So 3 significant figures. So let's write this to 3 significant figures now. And that would be 8,600 millimeters squared. And that would be the final answer for question 21 of this paper. With that in mind, hope you guys liked the explanation. Feel free to let me know if you have any questions. Please like, subscribe, and comment. If there are any other papers that you want me to do, any other specific exam questions that you want explanations on. Until then, see you later.